Okay. Exam stops at buffer. Everything after buffer will go to exam 3. Okay. I think we talked about polyprotic acid base a little bit last class, right? Compared to monoprotic acid base, which has only one proton that is available to dissociate or associate. Polyprotic acid base, they have multiple protons that can dissociate. For diprotic acid base, they can either donate or accept 2 protons. So for example, amino acids, and for all the amino acid, you have 2 protons. You can either have 2 protons accepted, or as a fully protonated form, you can dissociate 2 protons, right? Or our typical inorganic acid like sulfuric acid, carbonic acid, acetic acid. And so both of 1 and 2 belong to diprotic acid base. But the difference here, if you notice that for diprotic acid base, we can actually have 2 different forms. For amino acid, the fully protonated form H2B has a plus sign here. Okay, but for normal inorganic acid, sulfuric acid, and carbonic acid, the fully protonated form is the neutralized form, but their conjugate base. So for example, for H2SO4, it has HSO4 and SO4 2-, right? Well, for amino acid, H2B plus, then if you dissociate, if you donate 1 proton, it will be HB. And you can see that in this case, HB is the neutralized form. Well, the other one is not. Okay. And if you fully dissociate 1, what is the charge here? If you're losing 1 more proton, B-, right? So you see that it is a slightly different. This is minus, this is 2-, but they both belong to diprotic acid base category, right? Because the fully protonated one actually accepted 2 protons. You have 2 protons here. This one also has 2 protons here, even though the net charge is different. Okay. Okay. So the main problem we have to deal with today is how do you calculate the pH of the solutions of polyprotic acid base? For each species, it can have different forms, right? So for example, H2CO3, HCO3, and CO3 2-. So if your solution is starting with H2CO3, how do you calculate the pH? Or if your solution starts with CO3 2-, how do you calculate pH? Or if you have the intermediate form, how do you calculate the pH? That's the question we need to think about today. So I don't know why it doesn't. Let me stop sharing and share again. Okay. We talked about this one. This is an example of an amino acid, and you can have deprotonated form and fully protonated form. So there's 2 protons and the intermediate form. And there are 2 pKa's associated with this amino acid. And we call this one fully protonated, this one fully deprotonated, and this one intermediate. Okay. Now, so the question I mentioned earlier is, how do we calculate the pH in solutions of different forms? And this table is the table that you will have to be familiar with, because when you're seeing a problem, you will refer to this table, like whether it's a fully protonated form or fully deprotonated form, or it's an intermediate form. And when they are different forms, the formula is also different. Now, the simpler cases here is if you have the fully protonated form here, okay? For amino acid is H2L plus, or for an inorganic acid is H2A. And in this case, we treat them as monoprotic acid, okay? And the base for this, the reason for this is we assume that Ka1 is much larger than Ka2. So the effect of the second step of the reaction can be neglected, okay? Which is why we only consider Ka1 and treat it as a monoprotic acid. Same thing with the fully deprotonated form. We treat them as monoprotic base based on the same assumption that Kb1 is much larger than Kb2. Right? We will talk about this in details. Now, the complicated situation is when you have intermediate form. If you have intermediate form in the solution, you will have to use this equation for calculating the concentration of protons. And in most cases, you can approximate the pH as half of pKa and pKa1 and pKa2, okay? All right, so next we will go to each case and explain how it works. First of all, the example we will be using is amino acid, and this amino acid, we have the initial concentration. So this is our formal concentration, okay? We will be using F to represent this concentration. That's the initial concentration of the species in the solution. And it can have 3 different forms, okay? Leucine hydrochloride, sodium leucinate, and leucine. So those are 3 different forms. The first one is the fully protonated one. The second one is the fully deprotonated one. And the third one is the neutralized form, which is the intermediate one. Let's talk about the first one. And those are the pKa's, okay? The pKa values, the Ka values are given here. So you can see that Ka1, 4.7 times 10 to the negative 3, which is much larger than Ka2, which is 10 to the negative 10, right? And once you know Ka1, you can actually also calculate Kb, right? So how do we calculate Kb? For example, Kb1, Kb2. Still remember? Okay, so this one is 10 to the negative 14 divided by Ka1 or Ka2 if you're dealing with Kb1. Ka2 actually. The reason behind that is you have to look for that which reaction Kb1 is related, right? Because Kb1 is actually the first step of the association. So it's actually starting from L minus. So it's L minus plus H2 form HL plus OH minus. So this one is actually related to this one, which is why if you want to calculate Kb1, you have to use Ka2. And for Kb2, you actually use Ka1, okay? All right, so this is a brief